To my talk, I'm Cecilia Poletti and I'm working at the Graz University of Technology in Austria. And I'm very happy being here, and I wanted to thank Maureen, who is not here at the moment, for the invitation to this very interesting workshop. So I'm going to talk about dynamic recovery and dynamic recrystallization, so continuous dynamic recrystallization at large strains in aluminium and titanium alloys, and I will give some insights on experiments and modeling. So it's a very wide presentation. It covers a lot of topics. It's not going to be much in the depth, but if you have questions afterwards, of course, I will be very happy to answer them. So the first question that I did myself when I was preparing this presentation is why titanium and aluminium in the same presentation? And of course, I have my scientific answers, but the very first answers are both mainly used in rod as rod materials. So it means I have to have a method for forming them. They are used for lightweight design. So usually in the more or less for transport industries, but not only. And this is the topic that we are going to deal today, is we have grind refinement and texture, let's call them issues, which means basically they don't dynamically recrystallize in the sense of discontinuous dynamic recrystallization, and therefore we don't have fine grains with random crystallographic orientations in the final products. And these issues also have then some consequences in the applications as well. So I'm going to give a very, very short introduction on titanium and aluminium alloys because the public is very wide, and, but I hope I'm not going to bore you. Then a very short introduction of what is the meaning of high stocking fault energy materials, and then I will go to the topic, which are the experiments and modeling. So my background is experimental. I did experimental things for many years, and then I moved a bit into the modeling, and now I cannot imagine any experiment without model. And the other way around, I cannot imagine any model without experimental validations or explanations. So it's a bit a big mix of everything I did. So, you know, titanium alloys is used mainly for, as I said, transport lightweight design, also moderate high temperatures, but it's also used, as you have seen probably, or you know, the Guggenheim in Bilbao. So all these covered by plates made of aluminium, of titanium, sorry, titanium alloys, because of the high corrosion resistance. So the most important thing in titanium alloys, it's very similar to steels. If you know something about steels, then titanium is easy peasy. It's even easier because we don't have any eutectoid reaction. But we have this allotropic transformation. We have a HCP at low temperatures, which is not closed packed. It means it's a bit longer in one axis. It means we have a crystallographic structure that is not that bad for deformation. It also has some other slip systems that activate. And by increasing the temperature, then we transform into BCC. This is an BBC, sorry. So BCC, here is wrong. And by adding some alloying elements, we can stabilize the high temperature phase, and we can increase also the temperature transformation of this beta transfers, and we can have something like most of the titanium alloys have this type of configuration, so where you have the temperature and the beta stabilizing elements. Also you have alpha stabilizing elements like aluminium, for instance, here, would increase the whole or move the whole diagram upwards. And then you have a mixture, or you have a dual microstructure, so alpha and beta. So So a very complex situation for deformation. These materials are processing either in beta or in alpha beta. And this makes everything very complex when we want to understand it, control it, and then model it. Okay, so aluminium alloys, most of you know it. It's almost everywhere. So that's why I put it here. So very day-to-day examples. And this is one of my favorite products, to be honest. Not the fish, but the aluminium foil, because it requires a lot of steps, of rolling steps. So warm rolling, hot rolling, warm rolling. And then at the end, you cannot heat up again, take it from the furnace and roll again, because the heat transfer is very fast. Then you end up with cold rolling, and in between a lot of steps for recrystallization and also for precipitation. So it has a lot of complexities. And during these steps, you may have dynamic recovery during the deformation. If you do extrusion, then you may have very large strains, and in the interpasses, then you have static recrystallization. So you end up with a microstructure, which is very weird. And of course, I'm showing here profiles that I think everybody knows. All of them are made of wood here, I think. Oh, yeah, okay, good. This is also very clever. Good. So this is very general, so at least that you know what I'm going to speak about. And what they have in common is that they are high stocking fault energy materials. What is the meaning of this? The meaning of this is that if we have a perfect dislocation, this perfect dislocation can dissociate in two partial dislocations. And this configuration here does not allow dislocations to move. So it's very difficult to dislocation to go through stocking faults, first of all. And secondly, you lose the dislocations that move into two partial dislocations that are not moving anymore. The larger this distance is, the more stable the stocking fault is. And it means the larger this distance is, the lower the energy you have for forming stocking faults. So it's a very simplified interpretation of stocking faults and stocking fault energies. But basically, what you have is, if the stocking fault energy is very high, which means this is very small, the partial dislocations can reconfigure into a perfect dislocation, and dislocation can move as before without problems. And moving of dislocations is what you need for annihilation of dislocation, and moving of dislocation or dislocations that are mobile is what you need for dynamic recovery. So it means, I'm going to recall everything. It means that if the stocking fault energy is very high, this is very small, these partial dislocations can come together into, or these partial dislocations are not forming, are not stable. The dislocations will move, and you will have dynamic recovery instead of dynamic recrystallization. In the case of nickel-based aluminiums, for example, where this stocking fault energy is very low, stocking faults are forming, stocking faults, twins, all this. Even more weird stuff than stocking faults only. And this will avoid the movement of dislocations, and therefore it will prone to dynamic recrystallization instead of dynamic recovery. So this depends on the nature of material, and it's also not straightforward. So every material has its own specific stocking fault energy, which is also not constant with the temperature. So, and it's not constant, it depends a lot on the alloying elements. For instance, pure aluminium is a low stocking fault energy material, which means it will recrystallize. Or aluminium with a lot of magnesium, like the 5000 alloys. But most of the aluminium alloys with a low amount of magnesium and a lot of impurities has a very high stocking fault energy, which means It will dynamically recover. And the same happens with titanium alloys. All of them, or most of them, if you don't put a lot of alloying elements on them, I don't know what happens with high entropy alloys. Maybe you will know something in the future. But most of them are high stocking fault energy materials, okay, which means they will go in this direction. So this is when we start deformation, then we have cold deformation, density of dislocation increases. This is not what I'm going to cover in this talk. When we have warm deformation, at the beginning density of dislocation increases up to a small deformation. Then we may have either dynamic recrystallization or discontinuous dynamic recrystallization, like in nickel-based alloys, and dynamic recovery in our case. And if we go further with the strain, then we will have what is called continuous dynamic recrystallization or extended recovery, or many of the names that you can find in the literature. But basically, we are speaking about materials that during cold deformation they form cells. So they don't form stocking faults, they don't form twins. These cells look like this. So we have the dislocations at the cell's walls and spare dislocations within the cells. And during high temperature deformation, then the cells got, the walls get sharpened, and then you have subgrain formation instead of cells. Good. Oops, sorry. Come back. Oh, okay. Sorry. This doesn't supposed to be like this. Good. So the question how to refine the grain in high stocking fault energy materials is not new. It was done, I have to calculate, it's 60 years ago, the first time, at least in the literature, by Rosat. He was asking, is there any form of dynamic recrystallization in aluminum alloys or ferritic steels? By the way, ferritic steels also are high stocking fault energy materials. So you can imagine the same what I'm saying now, but for steels. Why I'm not showing here steels? Because I basically don't work on steels, but you can imagine the same for ferritic steels. Then in 1986, McQueen came with the idea of, yes, there is some type of recrystallization when these high-angle grain boundaries get flattened by the compression, for instance, and they get pinched off by the formation also of subgrains. And with this, I have a kind of what is called geometric dynamic recrystallization, which means you need a huge deformation to get very, very thin grains, plate grains, and then also formation of subgrains due to dynamic recovery, and then you have the pinching off of the high-angle grain boundaries and deformation. And later on, Montellier and Godet, they were working on what is called now continuous dynamic recrystallization. So this was, I'm pretty sure you already know, this kind of scientific fight between these two different theories that we think is not either this alone or this alone, but most of the time a combination of them. This also, the group of McQueen also splits, and they went on going in geometric dynamic recrystallization, and they call it extended dynamic recovery. So, but the name is the same, it's more or less. And here the idea is that the subgrains are formed, and these subgrains also are allowed to rotate. The dislocation increment is going into the low angle grain boundaries, so the misorientation between subgrains increases until you have the formation of high angle grain boundaries. So it's a very simplified interpretation of both. So when we want to study deformation at large strains, we think about experiments and models. The models are to, in my opinion, not to replace experiments. I think yesterday also in the workshop of Digimu, it was also given the same idea, is not to replace experiments. The models, we think them as to explain, a way of explaining the phenomena, as well as to reduce the amount of experiments or direct the experiments in one direction, but not to completely get rid of experiments. We need the experiments to explain and to validate, so both of them. Otherwise, we don't know what we are modeling. And this was one of the largest problem with respect to continuous dynamic recrystallization and titanium alloys. I'm going to show this afterwards. So in the experiments, so we want to get from deformation at large strains, we want to get the flow curves, of course, so stress strain, and the samples for further investigation. So this, you're laughing, but this is not sometimes understood. What did you do with the samples? I threw them away. I don't know the name. I changed. I mixed them. Okay, so the samples. You need the samples as well for in-situ microstructure investigation to obtain grains, subgrains, dislocation densities, texture, whatever you want to get from information. And which experiments? So for deformation at large strains, you don't have many experiments. You have hot torsion. This is a typical experiment. It's not a new one. You may have something in the industry, a similar hot extrusion or something like this. You are going to show something about max strains, or this is also a way of getting large strains, but in small steps. So you get a strain, then you have static phenomena, then a strain again, a static phenomena, strain again, a static phenomena. So you have a cumulative large strain, but not continuously. And microstructural features, you may have direct, so you see what the material, so you classical, you open the material and you take a look at it. So this is microscopy, any type of microscopy, mainly for dynamic recovery. We use a lot EBSD. I have a clock there. Okay, thank you. And then you have other methods, indirect methods. They are not much used. I know that Andras is working a lot on XRD, but also you may have differential scanning calorimetry to get account of stored energy, for example, or hardness. It's a very simple method, hardness, but gives a lot of information about stored energy. And of course, the question always in the middle, in situ, ex situ. Some things we can see after we did the deformation experiments. Some things should be observed during the experiment, and this is very tricky and not always easy. Not only the experiment, but also the interpretation. So I'm going to show only one of my favorite experiments, which is the torsion test, and we are doing it in a Glibel machine. I don't know how many of you know the Glibel machine. Yeah, 1, 2, 3, 4. Ah, a lot. Good, great. So you know all the pros and cons, or most of them. So it's fast. You can control the temperature very well because the thermocouples are attached to the sample. You can do in-situ water quenching, which is essential here if you want to study dynamic recovery. Otherwise, you will have static recrystallization during cooling, or metadynamic in this case not, but static, which occurs very fast. And in this case, this is here the sample. This is the sample holders, and this is one head is rotating infinitely until the material breaks. Depends You can heat up the sample by just direct current, alternative current, sorry, by the ohmic resistance of the material. Of course, if you put the thermocouple here, if you put the thermocouple here in the middle of the sample, and you start rotating, then you strangulate your sample. And okay, so this is not the best way. So you put the thermocouple on the shoulder. The shoulder looks like this. The sample looks like this. It's hollowed at the heads. And with this, more or less, you get the same area here than here, so section. And you get more or less the same resistance, and with this, more or less the same temperature. What we do is usually we just put thermocouples here, do heat treatments and calibrate until we know which temperature we have to control here or to set here to get here what we want. And the most important thing is to decrease the gradient of temperature here. So you don't want to have very large gradient of temperatures, because this gradient of temperatures then produce some flow localization, which is not desired. Yeah?
So you have a technical question. Your sample has this total length, or is only 20?
This is the total length is here. All of this is the same.
And you drill a hole to slide the thermocouple in?
No, the thermocouple is weld here, spot weld here on the shoulder of the sample. No, it's only this part. If the sample is good, only this part is deforming. And this is not deforming. But of course, you may have some difference in temperature between this point and this point. What you don't want is along the gauge a temperature gradient. This is what you don't want. And then you have the watersheds. These are positioned here. Okay. In our case, we have to also modify this a bit, because we saw that it was cooling down only from one side and not from the other. Good. If you have further questions on the clipboard, then I will be very happy then to answer them. So the first trials, please, on aluminium alloys showed something like this. So this is a light optical microscopy along the gauge. And this is EBSD. And what you see is that the microstructure is very heterogeneous. So we didn't cut as usual. People cut at a given percentage here, and then just only watch the microstructure to represent the global strain and stress values. What we wanted to do is we wanted to see the evolution of these boundaries. So here in blue you see low angle grain boundaries, and in black high angle grain boundaries. And you can see by increasing the strain, so the strain in the middle should be 0. In this case it's not, because the sample was not really aligned, but it must be 0. And then we increase the strain in this direction. But due to the texture of the material, we got this and some misalignment. We also got this very strange muster. And we also can see the evolution of the dynamic recovery, and then continuously transforming into high angle grain boundaries. And what you can see, everything is green, which means we have a very large texture. We produce a texture material. So then we decide to go to another material, and here is it's extruded material, so you will see some of the pictures I taken in this direction and some in the other direction, so of the grains. And we have deformation. This is a sketch of low angle grain boundaries at low temperatures. Then at one point we have deformation of high angle grain boundaries, and we assume that when we have a steady state here at very large strains, now we are speaking about above 5 or 10 of a strain, depending on the temperature and the strain rate, we have 100% of recrystallization, which is reached. Good, and this is how it looks like if I go to 350 degrees or if I go to higher temperatures. And you can see this is gauze, so grain orientation spread map. And you can see blue means low misorientation within the grains, and orange means high misorientation within the grains. So it goes for very, very large transformations until it really starts to dynamically recrystallize continuously. And since it's not easy to quantify the dynamic recrystallization rate here, or the recrystallization rate, what we are using is the fraction of high-angle grain boundaries. It's another way of counting how percentage of recrystallization or grade of recrystallization. So imagine that you only have high-angle grain boundaries, then you have 100% of fraction of high-angle grain boundaries, then you have 100% of recrystallization. And in the case of, so here you can compare, the fraction is 67% compared to 14% of recrystallization grade. So it's a way of counting this. There's no other way we have in this case. We also were trying to quantify metric necessary dislocations. This is what you get from the CAM maps. And this is the evolution for the as-received samples or as-received condition. And of course, the as-received condition is also in a mixture of dynamic recovered and static recrystallized structure. And by deforming at low temperatures, we increment the stored energy. So here is the geometric necessary dislocations density. So in this direction, you go to higher values of dislocation densities or stored energy, whatever how you want to see it. So in this direction, we are increasing. So this is also lower strain rate, higher strain rate. So we increase the stored energy. And when we go to higher temperatures, we also get into the other direction. So this is very typical. You will see this not only for large strains, also for low strains. You will see that you will increase the recovery in higher temperatures if you go in this direction, and you will increase the stored energy in the other direction. So we tried to do, we did successfully in-situ torsion test. Took us a while because it was difficult to get the proposal approved. Nobody believed that we could do this, and it took us very long until we could do this experiment. So what is the idea of this? We do torsion tests, and with this we get an incident beam that we did as flat as possible. So we have only one part of the sample very close to the surface. And as it rotates, of course, then you don't see always the same part of the sample. Okay, so you can see this also in the list diagrams. I'm not going to show them here, but I have them in the backup slides if you want. And then we applied the load. We applied temperature as well. That's why it looks like this. And through these windows, we could place the incident beam. We got the rings. With the rings also we got the list diagrams. I'm not going to show here. But we also could get the evolution of the crystallite size and the dislocation density. So at the beginning I was very disappointed because the crystallite size is not the subgrain size, it's not the grain size, it's an entity. And this entity is much smaller than the subgrain size, and it's only a coherent domain. It's very difficult to interpret and to correlate with respect to the EBSD data. So how we interpret this? We have even if you see it's made with hands. We have the static microstructure that consists on low angle grain boundaries, high angle grain boundaries, dislocations, and the coherent domain is the crystallite, which has a size defined by the previous processing. When we start the formation and dislocations, densities start to increase, so interior dislocations within the cells, the crystallite size start to decrease, and this is what we see here, this drop, and we see also the increment in the dislocation density. And this is for a very small effective strain. If you see here, we deform up to almost 3. But then when recovery starts, so these dislocations are arranged into low angle grain boundaries, and interior dislocations start to annihilate, then the crystallite size increases again. And the dislocation density decreases. Good. So there's also a question is, we know that we form the subgrains by the dislocations that are being accumulated at the subgrain structure, or the increment of the amount of dislocations at the subgrain walls. Is there any geometric dynamic recrystallization component? We don't have to exclude this, because the high angle grain boundaries here also move. And this is the material that I get from after hot rolling. So this is a very, as I said, the grains are very much longer, some of them are statically recrystallized, and we also have some grains with formation of subgrains, and this here with formation of cells, so it's a mixture of everything. So what we did is we took this material and we compressed in both directions, in this direction and in this direction, to see if there is a difference. And as you expected, indeed there is a difference. If we compress in this direction, then we have this microstructure. If we compress in the other direction, then we may have some pinching of the high angle grain boundaries. And as you can see here, for example, we have much more amount of new grains formed only by geometric dynamic recrystallization. This is only compressed, so no very large strains. And the same if we do it at higher temperatures. And as you can see, this should be. And as you can see here, again, we have much large amount of grains. So it means there are some geometric dynamic recrystallization components. We still are analyzing how important they are and what is the influence on the final microstructure. Okay, let's move now to titanium alloys. In titanium alloys, we know that we have this type of flow curves, which means typically dynamic recovery curves. For compression, this is very small strains. Also, if we increase the temperature, everything goes down, and this is sensitive to strain rates. And we know that if we do deformation, this is titanium 6-4. So when you cool down, you have martensite. It's awful for reconstruction. So you see that there is no recrystallization. This is cooled down. There is no recrystallization, so the grain boundary is moved a bit. They are serrated with respect to strain rate, so the low, or with respect to the size of the subgrain actually. But there is no recrystallization. We also know that from other alloys where we don't have this martensitic transformation, so we can watch what happens in EBSD in the beta phase. We have the high angle grain boundaries in black and the low angle grain boundaries in white, and we see substructure formation. If we increase the strain rate, we see also substructure formation in a very heterogeneous way. This makes the processing also of this material is very complex. And we also, if we reconstruct titanium 6-4, this martensitic, into the high temperature, so this is the martensitic transformation, we reconstruct now the beta phase. We also can see the formation of subgrains and the formation of probably new grains by geometric dynamic recrystallization or continuous dynamic recrystallization at the boundaries, and subgrains as well. So there is no discontinuous dynamic recrystallization in titanium alloys. And there are still a lot of publications because it's very difficult to get these kind of results where you quench immediately after the formation. Especially when you go to very high temperatures, it's very difficult to really quench and have in situ experiments. And this is important for us afterwards for the modeling. We are not modeling discontinuous dynamic recrystallization with critical strain and so on. And we may have grain refinement due to static recrystallization. So if I do deformation and 0 holding time at very high temperatures, I have something like this or nothing. But if I wait only 15 seconds, I already have a huge amount of recrystallized grains. So here more or less in the 40%. So that's why it's very difficult to get these kind of experiments and then to get into the phenomena. So, and we may have grain refinement due to continuous dynamic recrystallization. So what I'm showing here are experiments of the flow curves of compression test, the same I showed before. Now they look a bit weird here in this this scale. And the torsion tests. So in the torsion test, you may, the first thing you see is you have also an increment in the dislocation density, but we have a huge drop in the stresses. At very large strains, we have also a plateau. At this drop, we have some explanations for it. One is the continuous dynamic recrystallization. The other explanation is we have a texture modification, which deals to a Taylor factor modification. But these two things are not enough. So probably we have something else that we have to still understand. So here you can see the grain refinement after almost 6 of deformation at high temperatures, and this is in the 2 phases range. This is close to the 2 phases range. So sorry, the beta transverse temperature is 870 in this case. Good. Now let's go shortly to the interpretation and modeling. I have only 5 minutes. Okay, so I will then skip this. Good. So I would like to start with this and what we have done, and then I will show 1 or 2 results. So this is what you usually do when you want to express the stress as a function of the dislocation density, and then you use the Cox-Making equation. I think most of you know this equation. This is the hardening part, and this is the recovery part. So I'm going to tell why we are not using this. First of all, here you have the dislocation density, which means that all dislocations produce the same strain field. And this is telling us that dislocations are isolated, producing a strain field, and this has a consequence here, and that's it. This is not taking into account dislocations at boundaries where the strain field is smaller or forming dipoles. The second thing is age and air are usually fitting parameters. So they can be correlated to the temperature in a Arrhenius type. It can be phenomenologically, it can be correlated to the strain rate in the power and the strain rate with the strain rate sensitivity. But in any case, you need to adjust them, and there is nothing related to what is happening to dislocation or interaction of dislocations. And also here, as people also from and also here the precipitation contributions and all other half edge contributions are missing. So what we did is we start with this. Then we saw that for cold and hot deformation, one dislocation density is not enough. So we moved into the 3 dislocation densities, so at the walls, interiors, and mobile dislocation densities. Then we also implement what happens if the dislocations, if the walls start increasing the misorientation. So this is not included in rotas, it's included in the model of Montellier. Then we replaced the age and air, so hardening and recovery, by the Gonium equation. The Gonium equations are equations coming from creep. They are not coming from hot deformation. So they are very old equations that tells what happens during kind of dynamic recovery during creep or dislocation creep. It's not any creep, it's not diffusion creep. What happens with the interaction of dislocations? So there are rate equations that express if I am a mobile dislocation and these mobile dislocations get stuck somewhere, it becomes immobile. These mobile dislocations increases the dislocation density of the wall dislocation, it transforms into another. So it's a reaction type equation. So we introduced this, and of course we introduced the 2 phases for titanium alloys in an isopower way. And what is missing are heterogeneities, texture, and geometric dynamic recrystallization. With all this, we want to use the same internal variables, which are dislocation densities, sub-grain sizes. Grain sizes are not included. Grain sizes, sorry, are included. Particles and so on. These are all the internal variables. We want to describe hot deformation as well as creep. So we want to, dislocation creep, of course. We want to use one model for all these phenomena. And we want to use one model for all high stocking fault energy materials. So I'm going to show them. This is more or less what I already said. So we have the constitutive equations. Okay, I can leave it. I think. Why I'm so slow? And I want to show you a summary of the model. So for the model, we need as input the external variables, the strength parameters. We are not still in the position of calculating yield strength. Microstructure, initial microstructure, and initial materials parameter, activation energies, and high angle grain boundary mobility. The outputs are all these here. So it's not only the stress strain curves, it's also the microstructure, the recrystallization rate if we have the fraction of high angle grain boundaries. And we also have some glide and climb velocities as material variables. And again, we use the continuous dynamic recrystallization model as Montellier stat, combined with the Gonium equations from creep and uniform plastic power. Some results. Oops. So this is only up to small strains. So we can catch at high strains the softening of the flow. And we can also catch internal variables. Mobile dislocation density as a function of strains, immobile dislocation density, wall dislocation density, which are decreasing because we have continuous dynamic recrystallization. When the low angle grain boundary becomes a high angle grain boundary, then it disappears from here, let's say. And the most interesting part is we can catch the subgrain size. So first a drop and then an increment, very similar to the measurements that we have done of the crystallite size in the in-situ measurements. We can get the grain size as well, so the refinement of the grains. So you can think about extrusion processes. We get the fraction of high-angle grain boundaries, which if we start with a recrystallized material, then first decreases and then increases until we reach recrystallization. And with this also, this are only just zooms up to only one of deformation. And the same for torsion flow curves. Here we have some issues still to clarify. Okay, I'm very sorry that I was that slow, but what I want to summarize is we are dealing with high stocking fault materials, high stocking fault energy materials. They are going into dynamic recovery, followed by continuous dynamic recrystallization, but also geometric dynamic recrystallization can occur. We have texture changes, we have grain refinement at very large strains, and we can model it. And the model allows us to explain both the stress behavior as well as the microstructure behavior. So if you have any question, I will be glad to answer them.